Welcome back, everyone. Today we're diving into an explainer that is literally all about the universal glue of quantum computing. We're talking about quantum logic gates. These things are incredibly tiny, mathematically elegant, and honestly so powerful they are absolutely going to redefine the future of tech. So we're going to focus in on one specific, simple mechanism and see exactly how CNOT gates help build universal quantum circuits. Okay, so here's the big question, right? How do you actually build a quantum computer that can calculate absolutely anything? I mean, if we're just down there manipulating the probabilities of subatomic particles, how does that become a functioning machine? In classical computing, we just string together billions of transistors and call it a day. But in the quantum realm, the whole secret to achieving quantum universality comes down to a surprisingly tiny set of fundamental operations. And here's how we're going to break it down today. 1. Meet the CNOT gate. 2. Creating quantum entanglement. 3. Universal quantum circuits. 4. Optimizing gate complexity. And finally, 5. Real-world quantum processors. All right, section 1. Let's officially meet the CNOT gate, the fundamental quantum block. Now, to really wrap our heads around quantum gates, we kind of have to unlearn a little bit of classical computing. Think about a standard classical AND gate. If that gate spits out a 0, you actually have no idea what the original inputs were, right? They could have been 0, 0, 0, 1, or 1, 0. That initial information is literally erased. It's just discarded as heat. But, and this is absolutely crucial, in quantum mechanics, information cannot be lost. Quantum logic has to be perfectly reversible. Basically, whatever you put into a quantum operation, you absolutely must be able to deduce from what comes out. And that brings us right to the CNOT, or the controlled NOT gate. The way this little guy works is brilliantly simple. It manages 2 qubits, a control bit and a target bit. Here's the rule. If the control bit is a 1, it flips the target bit state. If the control bit is a 0, the target just chills. It does nothing. And the absolute magic of this, the control bit itself is never, ever changed by the operation. So our qubits get to interact cleanly without completely wrecking their super delicate initial quantum states. When mapping this out mathematically, just imagine the input combinations. For the scenarios where the control is 0, the target stays exactly the same on the output side. But if the control is 1, the target flips 0 to 1 or 1 to 0. Now, sure, it acts a lot like a classical XOR gate, but because that control bit is completely preserved on the output, every single piece of information is saved. It's a perfectly reversible 4x4 matrix. You can literally run the whole thing backwards and end up exactly where you started. Moving right along to section 2. Creating quantum entanglement, tying qubits together. So, single-qubit gates are great, but they basically just rotate a single qubit around. CNOT gates, on the other hand, are what we call entangling gates. If you take qubits that are in a state of superposition and feed them into a CNOT gate, it completely merges their fates. Mathematically speaking, the new state can't just be written out as a simple tensor product of the 2 individual states anymore. The information isn't sitting neatly in qubit A or qubit B. It's stored non-locally. It's in the correlation between them. They are fundamentally, permanently tied together. And the crazy part is, we can scale this concept up. Enter the Toffoli gate. You can think of it as the CNOT's bigger, beefier sibling. It's also called the double control NOT because it uses 2 control bits to decide whether or not to flip a single target bit. Why is this a big deal? Well, the Toffoli gate is essentially the reversible quantum version of a multi-bit AND gate. It is an absolute workhorse when it comes to the heavy number crunching needed for quantum arithmetic, especially when we start talking about algorithms used for code breaking. Which brings us to section 3. Universal quantum circuits, building everything from simple pieces. Consider this massive finding from 1995 by Baranenko and colleagues. They showed that any qubit quantum circuit can be decomposed into a sequence of 1-qubit gates and CNOT gates. I mean, wow. This brilliantly illustrates just how incredibly powerful the CNOT is. It's kind of mind-bending to realize that absolutely any complex, massive, multi-qubit algorithm you can dream up can be broken down into nothing more than single-qubit rotations and a sequence of basic CNOTs. Because of this, we get what's called a universal gate set. A super famous combo is the Hadamard gate, the T gate, and of course our friend the CNOT gate. By just multiplying these specific gates together in different sequences, you can approximate absolutely any unitary matrix on any number of qubits. With as much precision as you need, it's literally like having the 3 primary colors of paint. With just those 3, you can paint the entire infinite continuous space of quantum states. Let's hit Section 4, Optimizing Gate Complexity, the Art of Decomposition. Now, translating all that dense math into an actual physical circuit architecture is where things get really intense. Decomposing a highly complex 3-qubit operation takes a lot of engineering. The thing is, to make quantum computers actually viable, researchers can't just throw millions of gates at a problem and hope for the best. Every single gate introduces a tiny fraction of noise, so they have to synthesize these dense mathematical operations into physical circuits, strategically using the absolute minimum number of CNOTs possible to link the qubits together. And researchers will literally spend years mapping out these intricate physical pathways. They take these massive multi-qubit matrices, which are basically giant, terrifying grids of numbers representing the math of an algorithm, and they break them down into manageable, localized operations that the hardware can actually pull off. It's honestly a lot like untangling a massive, incredibly complicated knot until you're just left with one elegant, single string of operations. And we've seen some incredible milestones in optimizing this. For example, researchers Wei and Dai actually proved that a general 2-qubit unimodular orthogonal gate can be built using at most 2 CNOTs and 6 single-qubit gates. That is an optimal lower bound. And for a 3-qubit gate, it takes at most 16 CNOTs in the worst-case scenario. Hitting these low numbers with fewer CNOTs isn't just a fun math flex. It is absolutely crucial for keeping quantum errors in check before they completely ruin the computation. So, how does this actually work in practice? Section 5, Real-World Quantum Processors, Bringing Math to the Metal. Let's look at how this is executed on a real-world system, like Google's Sycamore processor. When they want to run a gate, they don't just push a magical CNOT button. First, they turn on the coupling between 2 physical qubits for just 10 to 20 nanoseconds. Just a blip. That allows a single photon to leisurely swap back and forth, creating a physical interaction they call an I-swap. The engineers then measure exactly what mathematical unitary this physical swapping represents, and they strategically compile those natural physical reactions backwards to force the hardware to behave exactly like our perfect textbook CNOT game. But then, how do they even know if it actually worked? Well, they use a technique called cross-entropy benchmarking. Basically, they pit the quantum processor directly against a classical supercomputer. They run a sequence of gates on the quantum chip to get their experimental probabilities, and then they crunch the expected theoretical outcomes on the classical machine. By comparing the two, they can zero right in on the fidelity of these newly minted quantum gates and pinpoint exactly where any coherent errors are trying to sneak in. And if we look even further ahead to the future of fault-tolerant architectures, we're seeing brilliant innovations like parity QC. Instead of relying on fragile physical CNOTs, these modern designs use parity codes to perform logical, parity-controlled knot operations. What's mind-blowing here is that they can connect an arbitrary number of logical qubits using transversal CNOT gates that rely purely on local operations. That means they can completely bypass the need for incredibly complicated lattice surgery just to move information around the chip, a total game changer. Which leaves us with this final, incredibly provocative thought. To run something like Shor's algorithm, which is the math that could theoretically shatter standard RSC encryption, we are going to need circuits packed with literally billions of Toffoli and CNOT gates, and they all have to run flawlessly. Every single one needs to be perfectly error-corrected. So mastering the physics, the math, and the engineering of these charming little CNOT gates, it's not just some academic exercise. It is quite literally the ultimate key to unlocking, or perhaps completely breaking, the entire future of our digital security. Thanks so much for joining me for this explainer. I hope it helped you see the quantum world with just a little more clarity.